So today I'm very excited to lead the discussion of a few papers on agentic workflows for systems research. And it really goes to my heart because I was a systems researcher and I'm still doing partially systems research. But like what frustrated me the most was the empirical side of performance optimization. And it was very exciting to see a lot of papers trying to tackle this problem heads-on by using this agentic workflows we've discussed in previous sessions to automate this process. So these are the papers I'm going to cover. So I picked the first one, and I realized that there was an immediate follow-up from their work, as well as the related papers from UT Austin. A disclaimer, so the reason why I picked those papers because they're from my friends, Audrey, Melissa, Rohit, and Divian Shu. And I really love their work, but I'm trying to be as objective as possible here. So in previous sessions, we've seen AI agents being able to find superhuman solutions to even mathematical problems by writing code, right? So this is the AlphaFold paper we've discussed in the previous session, where we have this agentic loop searching for optimal, better and better solutions. And the design paradigm in systems research has been like this. So this is a paper from Sitcom called Orca. So what it does is, given the TCP congestion algorithm, it uses a deep reinforcement learning model, an agent, to tune a knob of this congestion window, so CWND, right? So this single knob is the only thing it does. Right? And what this design, like automatic design paradigm or search paradigm, LLM-driven search paradigm gives us is the ability to redesign the whole policy or heuristics altogether instead of tuning knobs. And also, please feel free to interrupt me at any time if you have questions. Okay. It's supposed to be a discussion. And given this, this was the key motivation of the paper, Barbarians at the Gate. So they are saying that, we can actually save more than 40% of researchers' time by replacing two of the stages of this systems research pipeline. So typically we start from the problem formulation, right? And we formulate the problem, what the research questions are, and then we implement some evaluation framework, either simulation or real test beds. And then we design our solutions and test our solutions on the test bed. And we iterate until our solution satisfies some criteria we set, or it is we exhausted our budget. And then we write up our paper for the final submission. And they mentioned that the evaluation stage and the solution design stage consists more than 40% of our time. So what ADRS does is that they propose something called AI-driven research for systems, or ADRS. So they aim to optimize, or they aim to replace the two stages, so solution design and evaluation, with this iterative AI-driven search. So basically here, we no longer design the solutions ourselves, we specify the desired properties we want in our prompt. So prompt generator, giving to a prompt generator, and then this prompting with which context is fed to the solution generator, basically LLM, and the LLM is iteratively finding new solutions, injecting into some database, a database of solutions, and then we have some evolutionary search, selection criteria, selecting problems to be evolved on, and then this loop goes on. Okay, And by doing this loop, they claim that we can save more than 40% of our research time. Any questions this time? Yeah.
So it's kind of like a searching-based approach, right? Similar to our previous work discussed in the course. So like a brute force searching stuff.
It is a search paradigm, exactly. I wouldn't call it a brute force search because they still have some tricks up their sleeves. For example, they're using mostly evolutionary search, like the island-based search we talked about last time, and so on. But yes, exactly. So and they are using AlphaFold under the hood, right? You can think of their backend as AlphaFold like scaffolding around LLMs. Yeah. Great. So not all applications are suitable for this kind of approach. So they have several assumptions. So first of all, your problem has to be this empirical performance optimization problem. For example, scheduling, job scheduling, resource scheduling, caching, and load balancing. And these kind of problems have to be easily verifiable. So like I added quotes because this is not verification specifically in this in formal methods sense, but more of testing, right? So if the improvement and the correctness of your solution are easily testable by integrating your solution into an evaluation framework like emulation, simulation, and it's representative of how good your solution is, then this problem would be suitable to this ADRS design paradigm. And the evaluation has to be both fast and faithful, right? Both efficient and effective. So for example, simulation is very fast compared to emulation, but simulation might not be as faithful as emulation is. And I will get back to this point later in the talk. So, and they've demonstrated in their first paper, so Barbarians at the Gate paper, very promising results, showing that you can beat in most cases the state-of-the-art results from human-designed, handcrafted heuristics. So, for example, they show that by this telemetry repair task, they can achieve almost 10% better repair scores and 30% higher confidence. And they also tested on database transaction scheduling optimization, sparse attention design, as well as sparse instances scheduling in cloud computing. Okay, and as you can see, like with $20, several hours of LLM time, you can already beat those research papers, which was very, very promising. Okay. But there were several missing pieces when I was reading this paper, although the results were very, very promising. So first of all, like they only used OpenEvolve, right? Like there are more multiple scaffolding frameworks after OpenEvolve came out. So I was wondering, apart from GPT and also OpenEvolve, would other models provide better performance? And also their results were very heterogeneous, but kind of mixed, right? So there wasn't a clear categorization as to, or ablations as to what factors were the most impactful. So that's why they immediately had a follow-up actually later last year, so-called Let the Barbarians In. And in this paper, they did comprehensive and extensive evaluation studies across 3 LLM-driven search frameworks and 10 case studies. And they really went much deeper into the insights and the practice, like best practices on this agentic research workflow in terms of problem specification, solution evaluation, and feedback. So they tried out, first of all, OpenEvolve. So OpenEvolve is an open source re-implementation of the AlphaEvolve paper we've read. And it features this asynchronous evolution and code-centric pipeline. there's also something called GEPA. I looked into it. It is basically a similar design framework, but it's very prompt-centric. And what's interesting is that it has this prompt reflection mechanism. So instead of just discarding those invalid or suboptimal solutions, it uses those failed solutions to, in retrospect, what the LLM could have done better, and inject those retrospections or reflections into the prompt, telling the LLM what it could have done differently. And this has this Pareto filtering for retaining diverse solutions, and also ShinkaEvolve, which was similar. It has a very strong emphasis on sample efficiency instead of doing this parallel search over millions of solutions, hundreds of items. They emphasize the importance of sampling only a few solutions to come up with equally good or even better solutions. And here are some key takeaways from the paper. So first of all, they show that OpenEvolve is very strong, right? It's the strongest among all the frameworks they've tried and achieved top scores. ShinkaEvolve and followed by ShinkaEvolve and GEPA. And OpenEvolve was the most versatile in terms of the compatibility with different LLM models. And as I was expecting, there was real model sensitivity issue. So by replacing different models, you can get very different results. So in the paper, they highlighted how they get much longer programs from GPT-5 and much modular, because GPT-5 tends to use a lot of helper functions and design modular classes. And ShinkaEvolve, in comparison, has much shorter solutions. And also this combination between scaffold and LLM has effect as well. So for example, GPT-5 tends to produce longer and more modular programs, as I've mentioned, Gemini 3 gives much shorter answers. And what's interesting was that they highlighted this link between conciseness and the reliability. So I think in one of the experiments, they mentioned that Gemini really gives very short answers, really circumvented a lot of memory issues they were having with GPT-5. Any questions at this point? And what's interesting was one of the experiments, they showed this Hamilton moment, I call it. So they argue in the paper, like the barbarians with comprehensive evaluation, that LLMs don't just guess, right? They don't just randomly search or brute force search through the whole space. They're actually rediscovering those algorithms from unrelated fields. And they argue that it really transcends the human boundary, the domain boundaries of human experts. And this really goes to my heart, because I always believe that innovation often comes from connecting dots from related fields and applying approaches from different fields to the kind of field to see if the high-level idea really transfers. And the example they give was really this MOE, or mixture of expert load balancing. So given the demand distribution, how many replicas we should give to each expert, and how we place those experts on GPUs. And JEPA with GPT-5 came up with this solution very similar to Hamilton's apportionment, which was from political science. And they found this interesting parallel between the solutions the LLM search found and some approaches in adjacent fields. Questions? Nope? Okay. I really appreciate they were very honest about the failure modes. Although this was relegated to the appendix, but I find it's very interesting. They listed very explicitly what could go wrong. So they listed, for example, runtime errors, which consist of 1/3 of the solutions found by the LLMs. So these would be like syntax errors. These solutions wouldn't even run in the first place. And you have search errors. They mentioned something very interesting where you can. It's very easy to get into a stagnation situation where the model is finding something but oscillating between similar solutions without actually advancing the evaluation score. And there are also algorithmic solution failures, for example, overfitting to the underlying problem. So instead of developing new heuristics, novel algorithms, it's basically tuning some API calls or thresholds, static thresholds, in order to try to fit the evaluation workloads. And what's more interesting to me was that they summarized very systematically several best practices and tips around these failure modes to improve this ADRS research pipeline. First of all, they mentioned this in terms of specification and prompting. They call it less is more is less. So what does that mean? So it means that the prompts must be precise enough to be clear in terms of giving a clear problem definition, but not overly restricted. And they advocate for this prompt. So first we define the problem with the evaluation criteria and the context it needs. And it also recommends that we start from diverse and domain specialized baselines to prevent stagnation. So instead of just feeding the best sawdust solution, we also need some diverse solutions to inspire, so to speak, the LLM. And in terms of evaluation, this is very interesting because they mentioned that the generated solution is as good as the provided evaluator. And they recommend having diverse set of test workloads and safeguards, because what they do is that the interface is very broad. So in the prompt, they will provide the system code as well as the evaluation framework. So the LLM can, if they want, the LLMs, hack the rewards. So basically tuning in order to maximize the rewards instead of finding novel solutions. And the feedback was also crucial. So devil is in the details. Instead of having a single scalar feedback to the LLM, you should provide more detailed things like per expert, how that expert did, per trace, per workload feedback, as well as learning from failures. Instead of just say you failed, you should provide some feedback as to what could have been done better. And the central piece of the next paper I'm going to quickly talk about is the evaluation, right? It is the problems mentioned by the evaluation tip about overfitting to workloads and reward hacking. So because for me, I was a bit confused because whether they were trying to design some God heuristics that master all the possible different workloads. And to me, overfitting is good because the workloads are constantly changing, and also the interface between researchers and LLMs could be very broad. So we might not want the LLM to redesign the whole Linux kernel or the file system. Maybe I'm just interested in the inode allocation or not, only a small piece. So as I mentioned, ADRS might be too broad and too generic and can be brittle, inducing a lot of problems mentioned. And they are not shying away from the problems. They mentioned that ADRS works best for isolated changes with reliable and efficient evaluators. And it remains weak if you have, if you want to change multiple subsystems, multiple files. You want to change file systems. You might need to also adjust the memory management system and so on. So that's why I'd like to next talk about a paper from my friend, Divian Shu. They proposed a system called Vulcan. And what Vulcan aims for doing is that it tries to find so-called instance optimal resource management heuristics. So they want to overfit, so to speak, the heuristics to your workloads. Okay, if you are a data center, operator, then you only care about lossless traffic, for example. If you are a wireless tower, then probably that objective and workloads would be vastly different. So an instance is defined as a specific software or hardware platform configurations and paired with the workload. Okay, and I mentioned that there wasn't really one-size-fits-all heuristic. So in this case, on the x-axis, you have different cache optimization algorithms, and y-axis is the cache sizes, and the numbers represent how many traces that specific cache algorithm was performing the best. As you can see, there wasn't really like a dominant heuristic that performs best on all workloads. And as we've mentioned, now AI can develop better code and heuristics than what we can do handcrafting those algorithms. Yeah. So what Vulcan proposes is a more limited and restricted or narrower interface between the researcher and the LLM search loop. So they mentioned that generic code evaluation could be powerful, but can be brittle as well. And systems heuristics are not very amenable to this automated design pipeline. Why? Because the systems heuristics, for example, file management heuristics, caching, and like job scheduling, not only do they have a high-level intent, so what they want to do, right? I want to allocate, I want to schedule the next job that has the least amount of runtime scheduled so far, but also it is coupled with data structures, underlying implementations, right? So for example, the Linux CFS scheduler is coupled with this red-black tree implementation, right? It's not just the intent. And also this BFQ IO scheduler trying to balance between sensitive workloads and batch workloads by maintaining a set of per process or per process group queues for making scheduling decisions. So they argue that in real-world system design heuristics, we need to modify multiple files, and those modifications are coupled with the underlying implementation as well. So it's very challenging. It's not isolated changes. Any questions? Right. So they really propose this division of labor, and so if you can see, like this pipeline is very similar to what ADRS does, right? So you specify the scaffolding, but here we also have the specification for the instance itself, right? What is your workload, and you define your evaluation and the template, and then it goes on to the search process, right? This is in the process. You can also put AlphaEvolve here, finding candidates and using this evolutionary search, and then you have deployment. What's interesting was this separation of concerns, right? So here, the LLM's job is no longer just to design this all-powerful heuristic or algorithm. Its job is to, in this paper, they only target 2 types of heuristics. It's called value type heuristics and rank type heuristic. So this interface, so value type is, so for example, predicting a scalar, right? I'm predicting the congestion window size, that's only a scalar value. And then and ranking type, for example, scheduling, I'm ordering a set of processes, or caching, like which cache entries should be evicted next. And with this, and LLM is laser focused on designing only these 2 types of heuristics and not touching anything else. And we, as researchers, are responsible for designing not only the evaluator, but also the mechanism, the data structures, that the execution engine that consumes the decisions made by those heuristics. Any questions? Nope. And what's interesting was, to me, was okay. So now it's like we're going back from AlphaEvolve. This was very reminiscent of font search, right? For font search, we have very limited interface. You can only change this function, and AlphaEvolve was much more powerful because it could do a lot more than just editing a single function. But yeah, that was kind of interesting to me to see like how we are kind of rolling back the world of the history somehow. But they demonstrated, yes, so we were providing a much narrower interface, but this interface is still very expressive. So they surveyed more than 200 talks from OSTI and STI papers over the past 5 years, and they evaluated that, they argued that more than over 60% of the tasks are applicable. So their interface is applicable to more than 60% of the resource management tasks. And they give some examples. For example, DFS, dynamic voltage frequency scaling. This would be a value, right? What's the frequency it's setting? And cluster order scaling, like how many replicas, your pods, your Kubernetes containers you need. And also some ranking type of heuristics, right? Cache eviction, CPU scheduling, paging, and so on. Yes, so when I was reading the paper, one key question I was having in mind was how we define an instance, right? And they mentioned that instance is very specific workload hardware pair. For example, we can manually specify an instance, right? So this instance can be constantly changing. For example, by manually specifying the memory tiering for different applications. If you are designing kernels, then you might target different GPU types, A100, H100, for example. And in the paper, they argue that we could do this more generally by automatically generating an initial set of instances, so basically workloads. For example, cache sizes, and then characterizing those instances by some clustering algorithm. For example, k-means. So in this case, they start from some initial observations and during runtime, so they classified instances on demand, right? So given a problem space, given a set of observations, we see like approximately this workload was from this large or small cache size, and then given that, it dynamically chooses the heuristics for that specific instance. So it's like you have a classification of that specific instance, and based on that, you decide which heuristic to use designed by the LLMs. So it's like a bag of tricks. Okay? Questions?
Did they look at different instances, let's say for a specific workload but different hardware pairs, or a specific hardware but different workloads, as in trying to extract something that is common to them or not? Or is it like, to me, every time I see a specific pair, it just blows up in some sense, to all pairs. So I wonder if they talk about an instance, but I guess the whole approach is geared toward more doing overfitting rather than.
Yeah. So if I understood correctly, you're saying, if I find some insights with this small cache size, that could be applicable instead of starting from scratch, right? I see.
Do they talk about it at all? Maybe they didn't.
I would say their primary emphasis is still on like quote unquote overfitting to a specific instance, because they are like defining this instance optimal. But I totally agree. I think there should be a lot more parallels between those instances than across different domains. So like the learnings from one instance should be applicable somewhat, or could inspire like solutions to other.
Or maybe their whole point is that with it getting cheap enough or automated enough, overfitting many instances is better than trying to learn common knowledge, because that would require more manual work maybe.
Yeah, I totally agree.
Okay.
Yeah.
It's interesting because, as instructors or as teachers, we are trying to do the latter, right? We want to, in some sense, generalize and teach some common concepts, but it seems like the world is moving away to overfitting specific instances if they get cheap enough.
Exactly. I was actually, to be honest, I was a bit skeptical about this because this is like adding another layer of interaction. And what's interesting was, so the whole promise of ML and AI, especially in the context of systems, is that they are more adaptive, right? So they are more adaptive to changes in the workloads and so on. The downside is that they are black boxes. So whenever you have problems, it's really hard to debug and steer those models. I think now after a few days, I think I can appreciate more of this instance optimized solution, because yes, we're still like having this bag of tricks, overfitting to the problems, but now the adaptiveness comes from this switching, but this switching becomes more a white box, not white box, but more gray box kind of thing, because the heuristics are cold and they can be interpreted directly. But I think like we are still figuring out the design space with the LLMs. Indeed, this would not have been scalable if we were designing those heuristics.
For sure. Yeah. No, that's what I'm saying. They're in some sense leveraging the automation and adaptiveness aspects to, I guess, do more exploration or do more.
Exactly. Yeah.
Interesting. Is anybody here using LLMs for systems research, or the kind they're talking about? Okay. I guess you might be the closest one.
And maybe that's why I picked the paper. Yes. And
thank you actually for looking at other related papers that came out. Very nice.
Thank you. Yeah. So to give a quick summary of the evals of Vulcan. So here on the let me see, right hand side corner, you have this teasing clustering. So basically clustering different instances of cache sizes, different so-called workloads. And then on the bottom, you have the performance of different clusters. Here is that they are evaluating per cluster instead of how. I guess it would be interesting to see like the crossbreeding between different clusters, their approaches, and the higher the better. Right? Vulcan is in blue, and they demonstrated that the eviction heuristics can outperform the SOTA solution across all instances, and their memory tearing policies can also outperform the SOTA performance by almost 10%. And the total cost is like $40. You get state-of-the-art results already. Okay. It's very similar to ADRS, but narrower and in terms of like how they evaluate their heuristics. So a quick summary of the whole talk and what I took away from those papers. For Barbarians at the Gate paper, right? They show that it is a very clear and provocative thesis that many of the systems optimization, empirical optimization problems can be automated by this AI-driven discovery paradigm. Right? We really need to think, what we are really unique at in terms of this research space. And they also showed very compelling results, early evidence on the advantages of using this design paradigm over human handcrafted heuristics policies. But the first paper was mostly a feasible or position paper without very comprehensive and controlled methodological conclusions. The second paper, the Barbarians thing, really compensated was missing in the first paper by conducting comprehensive evals with providing very honest and mature bad practices and suggestions. But it still remains on the methodological side and doesn't solve the fundamental challenge of this evaluation bottleneck. Vulcan, on the other hand, tackles the problem from a slightly different angle by better designing this interface between us, researchers, and the design search loop. It has the strongest abstraction contribution, making the search more tractable and less error-prone. The challenge here is still, it argues that there is a benefit, and I believe there is a benefit to restricting the interface. Bless you. But still, it doesn't have this head-to-head comparison with ADRS in terms of like how many errors it can make less by using a narrower interface. Okay. Any questions? Nope. Some of my takeaways, here are my 2 cents. There are still a lot of open challenges. So what's interesting is, this fidelity efficiency trade-off, right? So in this evaluation, you can have the current design paradigm is still only suitable for this fast evaluation, efficient evaluation paradigm. But if you want to have some, GPU training on GPUs and more expensive evaluation, this would not be scalable, right? And excuse me, and this is still like localized empirical performance optimization. I was thinking, in formal methods, there are a lot of problems like cannot be simply evaluated empirically, right? There are properties you want to verify and equivalence checking, which is NP-hard. So it's not amenable to all the problems. And what's interesting was still this prompt engineering thing, right? You kind of treat those agents as your coworkers, and you try to give more helpful feedback to them, hoping that they could provide better solutions. And I think this problem is here to stay as long as we are working with agents for now. And it really got me thinking, who am I if I could be partially automated? I need to think about like moving from low-level implementation to better formulating the problems themselves, right? So that got me thinking, here's my advisor. The previous paradigm is that here's me, right? And we are all both tackling research problems. And now, maybe I have my agent, right? Or a whole bunch of agents. And my agents could have their own sub-agents, right? Helping me tackle my research problem. And my advisor could have her agents as well. So I think this is a really exciting problem, and it can get very philosophical down the line. That's all, and I'd love to take any questions.